Hello, welcome to Design Decode. So today we are going to talk about database sharding. So why is sharding required and how it can help us scale our systems? We are going to learn about those things. So let's start. So before we talk about sharding, we need to understand why it is necessary. As discussed before, we need systems to scale. So when we have a system that deals with a lot of data, we can't simply rely on one single machine to hold all the data in and make all the computation. So how do we solve this problem? Generally, the solution to scaling would be horizontal scaling and vertical scaling. So let's quickly understand what these two types of scalings are. So if we talk about vertical scaling, it means there is a computer which has some CPU, some RAM, disk, and other components. Now, when we want to expand this, we can increase all the capabilities. So be it the disk, RAM, or CPU, we can increase those resources, and that's how we can scale the machine vertically. We can scale it up. The issue with it is that the vertical scaling can be very expensive. As we all know, beyond a certain limit, the RAMs, disks, and CPU, everything becomes very expensive. And it is also becoming a single point of failure. Imagine there would be a lot of users that are trying to connect to your services, which try to connect to the same machine. And then if this machine goes down, then all the users lose access to your services. And that's, of course, not something we want. So what's the solution? The solution is horizontal scaling. So in horizontal scaling, what we do is we add a lot of copies of the same machine. So let's say there is machine 1, and then there is another machine 2, which also has disk, RAM, and CPU. And now when users try to connect to your services, then they can either connect to machine 1 or machine 2. So you can see, and there can be a load balancer in the middle, and that will route the requests accordingly. So you don't necessarily have to hit the two machines, but only hitting a single machine would do. So imagine what would happen now. If machine 2 goes down, there is still machine 1 that can continue serving your requests. Now, how does it relate to database sharding? We need to understand that. So what is sharding? Sharding is basically dividing data between multiple nodes. What do I mean by that? Let's say I have a table or a collection which is very big. Suppose I have 1 billion records. And let's say I have to add another 1 billion records, and I don't have enough disk space to deal with so many records. So what do? I need another machine to keep those other billion records. So in that case, the first 10 to the power 9 records goes to machine 1, and the second 10 to the power 9 records, 1 billion records, goes to machine 2. So imagine there is a library that has a lot of books, and at some point of time, we are going to run out of space for new books, right? So what do? We need to add a new building to the library and keep adding books there. It's the similar concept here. And yeah, it helps us keep the cost down. We have seen always that it is always cheaper to add a new machine to rather than vertically expanding the capabilities. By that I mean that making the disk space double, RAM double, and CPU double within a single machine is much more expensive than adding a whole new machine itself. So it helps us save cost and it helps us scale. Let's now talk about how we can distribute the data itself, how we can shard. So just recapping the previous slide, we have a lot of rows, let's say, and I have ID1, ID2, ID3, ID4, and then I have, let's say, a user table which has a name and surname, and John, Bob, Alice, Mary. And what do we do to distribute this data? First of all, the first strategy, key-based hashing. What we can do is, let's say we pick a key. It can be primary key, the ID in this case, and we calculate the hash out of it. And then we can use this function, hash of user ID, and then remainder with the number of shards. So let's say the hash of ID1 is 1, 2 is 2, 3 is 3, 4 is 4. Let's assume it's an identity function. And I want to distribute across two shards, shard 1 and shard 2. And what I do is I calculate the ID %2 because 2 is the number of shards. So ID1 comes here and then ID2 comes here. Let's say I assign this only for remainder equal to 1 and remainder equal to 0. So ID1 comes here, ID2 comes here, ID3 comes here, and then ID4 comes here. So going by the pros, generally event data distribution because we hash the keys and statistically that tends towards event distribution, but it can lead to hotspots. So let's say I query for the user John more. In that case, because the user 1 is in shard 1, many requests come to shard 1 compared to the shard 2. So what happens in this case is that the shard 1, it becomes overutilized in terms of resources, whereas shard 2 is underutilized. And that is not really good for cost perspective. Maybe we are over allocating more resources for shard 2 than necessary. So there is definitely room for improvement there. Then there is another strategy called range-based sharding, whereas the data partition by range of values. So let's say in this case, going by this, we can have rather like user 1, 2 in shard 1 and user 3, 4 in shard 2. If we say the range is 2, so that means 1 to 2 comes here, 3 to 4 comes here, something like that. And then there are other strategies as well, like directory-based sharding. Typically, the sharding strategy is very crucial to choose in the database. Generally, we try to keep the related data in the same shard. Let's say I query John and Alice often. In that case, I will try to choose a sharding strategy which will keep John and Alice in the same shard. Otherwise, we need to distribute the request to different shards, and ultimately we need to join something in the client, and that's not ideal. That leads to more latency. So what are the complications that can arise due to shards? So first of all, the joins become difficult, especially if the related data are on different shards. Then the joins become across shards. So let's say there is S1 and S2. I have U1, U2 here, U3, U4 here, and joining across these two data becomes very difficult. Actually, it can be some other table, right? Instead of U, let's say it's a table M, so M3, M4, and joining across these two tables can be very difficult because it is across network and because it is living in two separate physical partitions. The ACID guarantees, especially atomicity guarantees, are very weak in this case. There are, of course, workarounds there, which we can talk about later. Then the transactions, as I said, the ACID properties are very difficult to maintain. Then resharding and rebalancing, this is very important. So as I was talking about the hotspots, let's say one shard is way more used compared to another shard. And in that case, what we want to do is put some keys of shard 1 to shard 2. And to do that, there can be complications because moving these keys from one shard to another shard is not easy. And also, let's say from 2 billion records, now we are scaling up to 5 billion records. So going by the number 10 to the power 9 or 1 billion record per shard, we need 5 shards now. And in this case, based on the sharding strategies, maybe some of the records in these first 2 shards might need to move to these new shards, and that can become an issue. Although it is rare, but generally the issue happens when we need to scale down. So from 5 shards to 2 shards, if we make this transition, then it becomes very difficult because from these 5 shards, all the still existing data will need to move to this 2. And there are several strategies around it, especially consistent hashing, that we can talk about later. Then query complexity. Of course, the applications must be shard aware. The client needs to understand which shard to send the request to. If I want user 1, the client needs to understand that I need to direct my request to shard 1. If I need, let's say, user 3, then the client needs to direct its request to shard 2. And aggregating result is definitely slow because it is on the client side. And we make 2 or even more network calls, collect all the results, and then make some computation ourselves in the client side, which typically in traditional relational database without shard, it is very fast and handled by the database itself. And yeah, related to the point I discussed, sharding logic permeates the application layer. So yeah, it is very important to understand when to shard and when not to shard. So of course, when vertical scaling is no longer viable, it becomes very expensive, then we need to shard. And also when fault tolerance is very important to us, we need to shard because we can't afford a single point of failure as discussed above. And dealing with massive data sets, of course, it is important to distribute them across different machines and make sure the traffic load is distributed across different machines to perform overall higher throughput. When not to shard really. Sometimes it is very easy to over-engineer and optimize stuff even though the business use case is not there. So we first need to understand really what is the capability of a single shard, a single node, and we need to give it our best shot to make sure that the data we use, if it is really fitting inside one node. If it doesn't, then of course we need to shard, but of course the back of the envelope calculation and more thorough analysis are definitely good starting points to understand if we need to shard. For smaller data sets, it is not really recommended to shard. For fault tolerance, we can do something else, which is replication, which we will discuss later, but sharding is not really needed. We are unnecessarily adding just network overhead in this case. And if your application heavily relies on complex cross-shard joins or transactions, then as discussed before, sharding can actually slow you down. So yes, that has been an overview of sharding. Hopefully you enjoyed it. So if you like my video, please like, share, and subscribe, and see you in the next one. Bye.